All right, we have seen ones similar to this, so not only this was terrible, but I think we needed to, at least see when it's not just a sphere. So we have some kind of practice here, and especially before we go start talking about capacitance, which is what we're going to do tomorrow. Since a charge Q is uniformly distributed over a quarter circle of radius r as shown above, points A, B, and C are located as shown with A and C located symmetrically relative to the x-axis. Express all algebraic answers in terms of given quantities and fundamental constants. All right, not a problem. It says that rank the magnitude of the electric potential at ABC from greatest to least, with number 1 being the greatest, and if any 2 points are the same, give them the same ranking. Well, electric potential is going to be based on which one is closest. So I think we can all say that the electric potential at B is going to be the closest. So we rank that one number 1. And since A and C are symmetrically located the same distance away, they would be the same. But we have to justify our rankings. 3 points were given. 1 point was given for indicating that the potential at 1 has the highest, and another point was given for A and C being the same and ranked 2, and the third point was for your correct justification. And again, your justification should indicate why they're higher. Their example is compared to points A and C, B is closer to most and possibly all points along the charged distribution. And since potential varies inversely with distance, point B has the highest potential. Points A and C have the same potential by symmetry. So I think you only get the point for justification if you correctly indicate why B is greater and why A and C are the same. That would be a proper justification. 3 points there. All right, moving on to part B. So in part B, it says determine an expression for the electric potential at point P due to the charge Q. All right, so talking electric potential at the center. So this is a different location. They only gave 2 points total for this. And probably because if you've been paying attention a little bit, you understand that each point there is the same distance away from the center. And because each point is the same distance away from the center, even though we should add it up, we can just recognize that the electric potential is generally considered to be QK over R for points that were based on a electric potential of 0 at infinity, and it is a non-vector quantity, and so it's just related on how far away you are from the charge. Well, every point there is the same distance r away from the charge. So you could reason out that that's the answer. But if you don't like that, we could do it the actual way. We could remember that this is a quarter circle. So a quarter circle has a length of, an arc length of pi over 2. So if we consider this to be 0, this is negative pi over 4, and this is pi over 4. So we could do a sum of the potential, adding up each small point's contribution to the potential at point P. I would probably do this by taking dq and replacing it with something like dq equals lambda, the charge density, times r d theta. Lambda would have to be the total charge divided by the total length of this, which is a quarter circle, or pi over 2 times r. Tuck that away and substitute, and I'm going to get lambda r d theta divided by r times k, that equals dv. So I'm going to sum over the entire charge, which means from here I'm going to go from negative pi over 4 to positive pi over 4. And this should give me the total electric potential. So that's going to give me V. And then when I pull my constants out, which are lambda and k, the r's cancel. I'm going to be integrating d theta, which is just theta evaluated from negative pi over 4 to pi over 4, which is going to equal lambda k times pi over 2. Of course, can't leave it in terms of lambda, but lambda is q over pi over 2r. So if I replace that for lambda, I will get q over pi over 2r. The pi over 2's cancel, and I get q over qk over r. That's a little deceptive because of where the k is there, so the k was not underneath the radical there. So they gave full credit no matter which way you chose to do it. Obviously, reasoning it out is nice. It was only worth 2 points, so doing all this work that I just did probably killed you on time. Question C, a positive point charge Q with mass m is placed at point P and released from rest. Derive an expression for the speed of the point charge when it is very far from the origin. I am amazed that they gave this 4 points. That's just so much. Because this is a conservation of energy question and not a particularly hard one. So as a conservation of energy question goes, let's erase this to give us room to work over here and recognize we're going to place our point charge here. That's where Q is going to go. And the amount of electric potential energy it has is going to be equal to Q times V. That's the amount of electric potential energy. Assuming conservation of energy, at this moment, it has all electric potential energy. When we release it, its fastest speed will be when all of that electric potential energy is converted into kinetic energy. So QK over R equals 1/2 mv squared. And solve that for V. So V is going to equal the root of 2QK over MR. Now, I don't know how they gave 4 points for this, but let's see. They gave 1 point for any statement of conservation of energy. 1 point for correctly substituting in that the potential energy is QV here and it's 0 when it's traveled very far away. And for correctly substituting whatever you got for the potential here. So if you got the wrong answer but substituted in correctly here, you got a point for that. So there's 1 point for conservation of energy, 1 point for each of these. 1 point total for getting the potential energy right at both locations, and 1 point for correctly substituting in your potential, and then 1 point for solving for V. That is generous or gratuitous, I think, application of points. It's almost like they're running out of things to say. Question D, on the dot representing point P below, indicate the direction of the electric field at point P due to the larger charge. I'm really hoping no one had difficulty drawing a little arrow like that and labeling it E. It says for a vector drawn in the correct direction, horizontally to the right, 1 point. And finally, this is the moneymaker. Derive an expression for the magnitude of the electric field at point P. That's the one where I think there's some real work to be done. So, and they give 5 points for it. So let's take a look at that. It's kind of nice. I mean, if you made it this far, then you got 10 points so far, which is not terrible. But if you want all the points, this is where to go. And I'll talk about point distribution in just a minute, but I want to just talk about the solution to this and how we would probably deal with it, or how you might deal with it. In 2010, when this problem was given, the average score was 6.92. So students did pretty well on it. Across the board, when you looked at that particular year, only one question had a slightly higher average, and it was an RC circuit. So, not terrible. We got to find the electric field. So I'm going to pick just a piece of the bar, say right here. Let me grab something I can use for color. So right there, that's my piece of bar. and I'm going to call that dq. I've already explained how I would break the bar up into parts, so I'm going to continue that trend by saying that the amount of charge there is lambda r d theta. And let me go ahead and use capital R here. It produces a electric field here, and the electric field is at an angle, and that angle is based on theta. There is symmetry here, so the amount of electric field in this direction is going to be E cosine theta. And how we measure theta is important. I'm saying theta is measured from the center relative to where our dq is. And so because I'm dealing with a cosine, I'm likely going to have to do some shenanigans with my integral. But let's go ahead and build out our integral. This is calculating the electric field, so dE, and that's going to equal dqk over, I'm going to go ahead and just put capital R squared. We know that's going to be a constant throughout the course of this. So that's where I'm going to start. The next thing I'm going to do is recognize that I have to add this cosine theta to ensure that I have just the portion of the electric field that's along that line, that the cross portions balance out because of symmetry. So my next thing is to substitute in for dq, and so I'll have lambda r d theta for my dq. Don't forget my k, don't forget my r squared, and certainly don't forget my cosine theta. Now I have to choose my integral. I'm going to integrate over the entire bar to get the total electric field, but I'm going to break the bar up and do this from 0 to pi over 4 and multiply by 2, and that's because I have a trig function in there, and trig functions don't always behave well when you do this from a symmetrical point of view. So I think you'd always be best served breaking it up when you have some kind of symmetry like that. Now that's setting up the integral, and we know most likely the bulk of the credit probably came from doing that, but I don't want to stop there. I want to continue. So in order to continue, I'm going to do the integral, although probably only a point or so is given for doing the actual mathematical work. So let's pull out all the constants, and there are a lot. 2 lambda k over r, those are all constant, and I canceled out one of the r's, and I'm left with the integral of 0 to pi over 4 of cosine theta d theta, and that's going to equal the electric field. Not terrible. Most of you at this point, we've done this enough times, and calculus or not, you guys should all know that that's going to be sine theta. And we're going to evaluate that from 0 to pi over 4. Now, if we had actually left it as negative pi over 4 to pi over 4, this one would have worked just fine. But I still think that you're always best served when you have a trig function to, if you can, break it up into parts, because you'll probably be happier if there's a problem. Kind of done now. I'm just going to plug in my final results here. This is going to be 2, and we know lambda already. We've done lambda before from the prior part. Lambda is the entire charge of the bar divided by the entire length of the bar, which is pi over 2 times r. So I'll do the same thing here. I'll have q over pi over 2 times r times k over r. And here it's going to be the sine of pi over 4 and divided by, minus the sine of 0. So the sine of pi over 4 is just 1 over the square root of 2. And that's really it. I know you guys don't like this, so let's write this as the square root of 2 over 2. You like that better? And let's bring it all together. So let's see. This 2 and this 2 cancel. I get an r squared. I'm going to be stuck with the pi in the denominator, so it looks like 2 root of 2 qk over pi r squared. All right, so points. They gave 1 point for any indication that the total electric field is the integral of all of the horizontal components. So it's funny because they just indicated that it's all the horizontal components, but they didn't give a point for, I'm sorry, they gave 2 different points for this. They gave 1 point for indicating you have to integrate all the pieces, but they said integrate the horizontal pieces. But they gave a separate point for recognizing that the cosine is how you will get the horizontal pieces. They gave 1 point for changing the variable to something you can integrate. In our case, changing it to d theta from dq. And so there's another way to do this problem if you do it by arc length and location, but I really think you had to do it this way. You had to work theta in order to make it work with the cosine. They gave another variable, another point for correct limits of integration. I chose 0 to pi over 4, but multiplied by 2. If you had done negative pi over 4 to pi over 4, you would have gotten full credit, and 1 point for the final answer. 5 points there. So there's a lot, but I think that's a solid performer. So that's it. I hope you guys followed along with that. Look, you've got my AP work that you should probably be doing. I'm not overloading you right now, but you should be doing the my AP. This was 15 minutes of reviewing a problem, so I would argue that that wasn't too much, and I do want you to submit your graded answer this evening. But I've posted all the my AP. I am going to be setting it up so that there's a place for me to add grades for doing the my AP. Grab Unit 1 or Unit 2 multiple choice and start on it, please. So get started on that. The review here is going to have to ramp up in difficulty now, and so we can't be messing around. Take it easy. Have a good night. Bye.